Well, I'm Matt Leonard, and I'll be your host for the last session of the conference. I think of it as the ultimate session. And our first speaker is Matthew Hayes.
Is it on now? Yeah, okay, good.
And he's going to talk about some stuff.
Thanks for that so generous introduction, Matthew. So, hi everybody. Welcome back from the beach. So I am going to, well, first of all I've got to thank Polis for upgrading my talk from 15 to 30 minutes. And I think this is the title that I was given, and I understand now that the upgrade in time was to allow me to say the whole title. But this is challenges and opportunities towards an observational and theoretical input towards a better understanding of the Lyman photon production and escape across the galaxy assembly history. An opinion review talk that basically boils down to a collection of random but hopefully correlated thoughts that I've put together over the course of the meeting. And here's a list of all those thoughts. I'm going to talk about predicting the ionizing escape fraction at high redshift based upon things we've been doing with Lyman-Alpha, understanding how much mechanical energy in ionizing radiation is being produced by stars, the importance of getting the nebula line ratios correct, particularly in the ultraviolet. Looking a bit further into the UV, I'm going to talk about making sure we really understand the distribution of dust and its effects for interpreting the ionizing output of galaxies. And I'm going to present a crazy conjecture about what green peas are. So if you'd have asked me recently how to predict the evolution of the Lyman photon production across cosmic time, I would have said it's really easy. You just go and look it up from this paper that we published 7 years ago. It's really nice, I realize now that 5 of the 6 authors are actually at this meeting. And we found in 2011, by just comparing the UV luminosity functions with those of the Lyman-Alpha, that if you look in the local universe, the sort of integrated, what we call then volumetric escape fraction of Lyman-Alpha, this is how much Lyman-Alpha is being produced per co-moving megaparsec. This varies as a really strong function of redshift. From below the percent level we thought, probably it's a little bit higher now in the local universe, but by the time you get to redshift 5, it's gone up by 2 orders of magnitude. And we did this in a really, really simplistic way, just by taking the intrinsic Lyman-Alpha luminosity density that we get from all of the Lyman break galaxy dropout surveys at high redshift. We fold them into the star formation rate calibration to get the sort of intrinsic star formation rate density of the universe, and then do the same thing with Lyman-Alpha, and we take the ratio, and then we're done. But this is assuming a large number of things, and it gets very complicated if you start to look under the hood, in that it's assuming that there's a constant ionizing photon production efficiency, which implies constant IMF, stellar metallicity, binarity, star formation history, a constant reprocessing of exactly 68% of all the ionizing photons into a Lyman-Alpha. And probably all of these things vary with redshift, in one way or another. Still, I think it could be a very valuable approach. What we're going to do with the Lyman continuum, well, Inouye has ruined this for us in the sense that beyond redshift 3, 4, this is not anything we can measure directly. These are just the sort of transmissivity of the universe as a function of galaxies given at high redshift. This is the redshift 4 curve here, and by the time you get all the way down here, you're looking at transmitted fractions of just a few percent. So we're all stuck to can't do this kind of stuff with the ionizing continuum out beyond redshift 3. So this is where we start to rely upon lower redshift star-forming galaxies to act as calibrators, which has been, the motivation for many of our low redshift projects with HST over the last, since HST was launched, I guess. But this is what Axel showed a few days ago now. This is what we've been doing for Lyman-Alpha and how we think that we can predict the Lyman-Alpha output. We have a large number of observables in our galaxies, and many other surveys have something comparable. And by doing this multi-parametric linear regression study, it's relatively straightforward when to apply these methods, then we find that for all of these quantities that we've measured, that If you want to predict the Lyman-Alpha luminosity, you've got to get the far ultraviolet luminosity. That's really important. And the far ultraviolet size, the size of the star-forming regions, also seems to be very important. And then some other quantities, oxygen 3, and then these are all ranked by how important they are. And that allows us to predict the Lyman-Alpha output, Lyman-Alpha luminosity, pretty precisely, right? We capture more than 80% of the variance in this sample using this method. And so ultimately we plan, I guess, to do exactly the same thing with the ionizing continuum when those data sets exist. And so I think we're at the stage right now when there's about 30 known Lyman continuum leakers. Not all of this information is in place for all of them, but it feels like with a really considerable effort with the Hubble Space Telescope over the coming years, when we come to Crete for the 2020 meeting, this is something that we could hopefully be able to begin doing. So what we'll have to do, of course, is just replace those quantities with the things that we believe to be important, whatever. You know, the UV luminosity is probably going to correlate somehow with the ionizing output. And we've got these standard things that we've talked about all week, the Lyman-Alpha profile, the O32 ratio, the depth and the equivalent width, covering fraction, and whatever. And at the highest redshifts, perhaps we'll have to modify the way we think about Lyman-Alpha a little bit. If the blue wing is going to be absorbed by a neutral intergalactic medium, we might have to rely upon something that's not the peak separation, but I'm sure there are proxies for that, like the velocity shift and maybe some width-related information. So in Stockholm, since in Stockholm we've been working a bit on this project to estimate the well, it began with as a feedback project where we wanted to calculate how much mechanical energy has been injected into the interstellar medium. And the goal of this was to try and solve this, well, it's been presented as a puzzle, so it's how can galaxies be Lyman continuum leakers if they're really, really so young? And of course I write puzzle in quotation marks because it's not really a puzzle. I think we know the answer, but this sets the stage relatively straightforwardly for it, I think. This is the output of various different starburst 99 tables. This is the age of the stellar population for one instantaneous burst on the x-axis. And on the left y-axis, you see the logarithmic rate of ionizing photon production by this stellar population. And this is spanning 10 decades in ionizing emissivity, or in number of ionizing photons. And you see that here, this is basically constant for 4 megayears, or roughly, after which it begins to decay extremely rapidly. By 7 megayears only, you've lost 99% of the ionizing photons. And if you believe you have to shift, to break up the interstellar medium, or drive out winds, or introduce a lot of turbulence to the ISN, that's going to take some time. We need to wait for the supernovae to go off. On the right y-axis over here, we have the logarithm of the mechanical energy that's been injected into the ISN since this time of zero, and it starts down here. This is now covering 4.5 decades top to bottom, and by the time you've lost 99% of your ionizing photons here, you've only recovered 1%, or no, 1/10 roughly of the mechanical energy that's available completely. And this has been the argument we've used to explain. This is the Lyman-Alpha spectrum of the very young SPS 0335 galaxy that Christian has a poster on out there in the entrance hall. And this is one of the strongest emission line galaxies that we know about, and its Lyman-Alpha looks like this. And the argument that we've been using for this is that it's so extremely young. And it's pre-supernova, and all of this gas is basically static. So we wanted to examine in more detail the stellar populations and see how much room there is in the available information to hide some aged stellar population underneath what's already there. And so this is what people do. We model a stellar population like this using sequence of population synthesis. This is just high-resolution starburst 99 models. You can do this. We model the metallicity and the star formation history. And then what other people do is strap all this to photoionization models to predict the nebular line fluxes, also in the optical forbidden and permitted recombination line. And then this has been very successful. I've been very impressed by a lot of these studies, but the helium-2 is still remaining a problem, it seems. We've heard quite a lot about that at this meeting as well. So the sort of input of this model, or the features that we're really sensitive to, are mainly these these P Cygni lines of oxygen 6, nitrogen 5, carbon 4 that form in the far ultraviolet. These are just the Starburst 99 models, the high resolution ones. And they turn on as a function of, they begin when the starburst is very young, and they're very strong, and then after 7, 8 mega years, they become very small. But what comes in instead are these stronger absorption lines, particularly of carbon-3, silicon-3. And they dominate between ages of 10 and 30 million years. So what we wanted to do was to estimate the recent star formation history and see what that would mean in terms of mechanical energy and ionizing photon budgets. To do this, we looked at a sample of star-forming galaxies observed with COS. I prefer anything that's been observed in 2 wavelength settings, G130 and G160M. So that gives you both the, usually more than one of these lines to look at. We perform a lot of simultaneous modeling of these populations, including the SDSS spectra. And this is nothing that many other people don't do. I mean, it's a very common approach. We're just fitting populations of stars with dust. And we input both simple stellar populations, the standard 1 burst situation, constant star formation rates, and multiple bursts. And in this case, actually, we're looking at we're limiting that number of bursts to 2. And if you look at how star-forming galaxies are, it's full of star clusters. They didn't all form at the same time. There's some, a spread of 20, 30 million years in how this starburst got ignited. And we should see some of those features coming back in the ultraviolet. And the original motivation, as I think I've said now, but I will say again, because I have a slide, is that we look at these green pea galaxies. They have these extremely strong nebular lines. They're very low mass, low metallicity, and they're booming in Lyman-Alpha. They have specific star formation rates about as high as anything we know about. And you look at their Lyman-Alpha, and they look like that. And if you look at the blue compact dwarf galaxies, they have these nebular optical spectra that look like this. They live in these big balls of gas. They're also, all of these quantities are basically the same until you look at the Lyman-Alpha and it looks like that. And we wanted to know why. So these are just some pictures of the fits. This is just the recovery of the nitrogen 5. That will be the nitrogen 5 P Cygni there. And what this means in terms of the number of hydrogen ionizing photons is this. So this plot's going to get quite busy in a minute, but I've cut some of the nasty parts out of it for now. This is time ongoing from beginning of star formation rate episode on the x-axis. And on the y-axis here we have the number of ionizing photons. And these different colored lines here, they just represent different star formation histories. So in the cyani line up here, that's the one single burst of star formation that turned on roughly 3.5, 4 million years ago, and it's always going to turn out to be that line because we end that time because we have to reproduce the P Cygni lines in the ultraviolet. And after the 4 million years that's been around for, it's lost half of it. But it's coming out here, it's emitting this many ionizing photons per second, or producing that many ionizing photons per second at the time which we observe it. And this growing line here is what you get for a constant star formation rate. It reaches up, it's almost coming to equilibrium after 8, 10 million years. But if you look at what happens for a combination of bursts, this is what this is 2 populations of stars here, and this turned on 23, 24 million years ago. And of course the ionizing photon output decays, as you expect it would. And then when the new burst forms 3, 4 million years ago, then it just goes up again. And all of these things, of course, are basically the same here at time equals time when we're observing the galaxies, because you have to match the non-ionizing UV. But then, if you look at what this means for a mechanical energy injection, you see something very different. So here is this is for one burst of star formation and the constant star formation rate again, and it's the log of the mechanical energy injected on the right y-axis here. But if you look at what this one has been doing, it's been hanging around forming stars now for 25 million years. Well, with massive stars around for 25 million years, so that adds up to an awful lot of supernovae that have gone off. And this is able to preheat the interstellar medium. This is probably able to drive out strong galaxy winds, able to let your Lyman-Alpha get out of galaxies. And if I look at what happens just by comparing 1 and 2 bursts of star formation, I get in this sample of 35 galaxies that we looked at this many. The orange histogram here is the one simple stellar population fits, where we see and the black one for 2 is shifted out to by about a factor of 3 on average. And so we believe, or I believe at least, that there's all of these COS data, particularly when modeled with optical spectroscopy as well, there's a lot of room to hide recent star formation underneath what we see. Underneath what you see just by looking at the UV alone. So what this means for the number of ionizing photons that are being produced, this is what you expect for, this is when I compute always on X the number of ionizing photons for hydrogen computed from H alpha and H beta, and then I compare that with the number of ionizing photons being produced by the stellar models. When I do 1 population fits, we see something like this. When we do 2 population fits, we see things that look an awful lot better. Looks kind of like that, basically getting there with the with 2 populations of instantaneous bursts, and the constant star formation rate is rubbish. It's really badly overproducing the hydrogen ionizing photon rate. Now we also have a number of helium-2 nebula helium-2 lines in these spectra, the 4686 line and the optical, and we can do the same game with some rather basic assumptions about how much helium-2 is getting ionized, and that's the same crap for a simple stellar population. And this double stellar population worked really well for H alpha, but it works terribly for the helium-2 line. But what does work for the helium-2 line is when I let the star formation just run on and on. The constant star formation rate fits really get the helium-2 looking quite nice. So clearly something is up in the star formation histories, or this is not exactly what's correct, but I'm quite hopeful about at least soon with some new models being able to reproduce the helium and hydrogen ionizing photon rate simultaneously. I would like to talk a little bit about if we're looking at the right wavelengths, and it seems like I'm not the only person to have had this thought. So when you look at the ionizing continuum with HST cos, you're limited by 2 things, right? You have to have the galaxy at least out of the rest frame of the Milky Way, so that all of the ionizing continuum doesn't get absorbed by H1 in our galaxy. But really, you have to wait until cos becomes sensitive at wavelengths about 1150 angstroms, which restricts you to the redshifts around 0.3. This is what's been done, particularly with all these Lyman continuum leakers, the isotop samples. And if you wanted to go further out in the UV, that would be nice. But you have to fight against the decaying sensitivity of HST cos, which means going to high redshifts. Means going out to redshifts 0.5, 0.6 or something like this. Galaxies become further away and get more expensive for that reason. But again, if you get the extreme ultraviolet ionizing continuum correct, and you find galaxies that are really producing a lot of helium-2, you know there's going to be an awful lot of helium-2 ionizing photons around, and this may well compensate for some of the problems that you experience by going to higher redshifts. And the same thing is true on the redshift 3. We're limited by the IgM cutoff. The IgM on one side and the atmospheric cutoff at the other side limits us to about around redshift 3. We can go a bit lower in redshift using HST in the ultraviolet. But again, we're limited to measuring Lyman continuum very close, usually, to the Lyman edge, around the 912 angstrom spectral break, and then a few tens of angstroms to the blue of that. But if you look at the ionizing spectra of, well, black bodies that look like this, this is the wavelength here, and you have a bunch of black body spectra here. I don't have any spectral model, so I just used some black body formulae and computed what the spectra would look like, and then normalized everything at the Lyman edge here at 1 Rydberg. You see a huge spread here in the number of photons at 2 Rydbergs, and this is not realistic models. This is purely for illustration. But if you look at the things shown earlier in the week, they seem to be rising in similar kinds of ways. But if we want to constrain the intrinsic Lyman shape of the Lyman continuum, we want to be able to observe this stuff down here. And it may help quite a lot in terms of estimating the Lyman continuum escape fractions. As we know that the cross-section for hydrogen looks like this, where you have the cross-section at the edge there, and this run falls off then as frequency to the 3rd power with increasing frequency. And this it goes into the optical depth like this, which this third power here ends up in the exponent up here. And you see that this is a line that I overplotted for a tau of 3, and that tau of 3 was selected to give us a 5% escape fraction here at 912. By the time you get to 2 Rydbergs, that's gone up to what looks to be about 60% getting through. So if you take this and if you take the intrinsic spectra and combine them with with what would get through the interstellar medium, you see lines that look like this. This is now just the black line multiplied by the intrinsic spectra. And you see an enormous spread up here. And if you have galaxies that are producing large numbers of very hard ionizing photons, the spectrum up here is tens of times brighter than it is at the Lyman edge. And I don't say this isn't very challenging, but there could well be a sweet spot in Redshift where things like this become possible. And of course, I wasn't the first person to have this idea. There's a paper from Stephen McCandless and John O'Meara from a couple of years ago that says exactly this. And because of this optical depth that peaks right by the Lyman edge, it says here that they caution that the escape fractions that we have measured are possibly extreme lower limits, and that the escape fractions could be intrinsically very much higher. But as we said in the discussion earlier on, if it's all covering fraction and not a low column density system, then none of this will work at all. But that would be also quite a constraining result in itself. So there's that. I want to talk a little bit also about the distribution of dust in star-forming galaxies, because this came up also a couple of days ago when we were talking about measuring. Well, my motivation for this came from talking about the output of ionizing radiation, or estimating the intrinsic ionizing photon rate from H alpha and H beta. And somebody said, I forget who, that if you just correct the H alpha, then you're good. You know how many ionizing photons are being reproduced into the H alpha, and that's fine if you know what the extinction law is, and if the dust behaves as something that's input into an extinction or attenuation law, which is basically a screen, or a mixture of stars and or an even mixture of dust and stars. But dust can be clumpy. I'm sure that's a possibility. It can be distributed in clumps all around the galaxy, particularly in star-forming regions. Everything seems to be pretty clumpy. And if you introduce, this was a cartoon from the Calzetti 1994 paper, just illustrating this clumpy dust scenario. You have an extended surface of stars there and some clumps in the way. And that changes the way the extinction law behaves completely. So these are some line ratios in a paper by Claudio Scalata from now almost 10 years ago, where we plot the Lyman-Alpha to H-alpha ratio and the H-alpha to H-beta ratio. And these galaxies are all over the place. Sometimes Lyman-Alpha is being preferentially suppressed and is weaker than you would expect from the recombination value. But there's a large number, and this solid line here is a symbol screen of what you would expect from the intrinsic line ratios modulated only by dust. And there's a huge bunch of galaxies that fall above this line, and there's a number of interpretations for this. But but this could be purely dust, the effects of a clumpy, dusty environment. And what happens when you have a number of dusts along the line of sight, each with its own column density tau, then what you get as you tune up the optical depth is something that follows this screen law for a while, and each one of these dotted lines then deviates from it and curls back around. And when you make the optical depth really, really high, you end up back there again. You haven't affected any of the colors, but you've affected the amount of dust, the amount of light that gets through this screen of bricks, basically. And if the situation is something like that, then what you have is a situation where you measure no dust attenuation or very little dust attenuation. You have a huge variety of optical depths in your galaxy. And the H-alpha, H-beta correction fails to give you the intrinsic Q. So I think this is something that we should pay more attention to. I think it's something that you can train observationally as well by including more than just H-alpha and H-beta in the dust corrections. I think that's also something that's worth looking at. I want you to say that. All right then. Okay. These are green peas. Okay. This is a conjecture that I'm going to make. I don't have any support for it, but in the questions you have to tell me why it's not true. So we know that green peas have extremely strong nebular line spectra, and they have very little dust. And the green pea looks like that, and it results in my, that's O2, that's H gamma and 4363. Yeah, you recognize it, right? And it looks like that, and it's blue. And it's tilted like that for a point. I'm going to say now that green peas aren't this green ball here, but they're very compact versions of this. So they have a host galaxy. And what we find, if you look at them from the, what I'm going to say we find, if you look at them from the polar viewing angle, so you look down into the system, this is all very small, right? It's small disky things. You can't resolve them from, you can't resolve any underlying host galaxy in the Sloan Digital Sky Survey, and the available HST imaging is all pretty shallow. So the available HST is a bad low surface brightness telescope anyway. And my conjecture is that these green peas, they all have a host galaxy. And you look at them like that. Now, if you tilt this round, this is what I said the other day in one of the discussion sessions, and look at it from the side, you see something that looks like this. You suppress the emission lines that are all being produced in the middle, and you lower the equivalent width, and they no longer get selected as green pea galaxies anymore because the oxygen 3 lines are not strong enough compared to the continuum. What you do is preferentially select galaxies that are face-on, and you look down right into the ionizing stars, and that's why they're Lyman continuum leakers. I have this slide. So in Stockholm next year, we're organizing a 4-week workshop on the interstellar medium. It's doing many different things. There's going to be some Lyman-Alpha there, but there's a lot of alpha molecular gas stuff and a lot of high redshift stuff, ionized ISM. They're all falling in different weeks, so it'd be very nice if some of you came and registered for our meeting in Stockholm. There's these guys, because they're always here. And here's a summary of all the things that I've talked about. So we will use low redshift galaxies to calibrate the ionizing emissivity of galaxies. By doing these things that I discussed, we don't need to actually know what psi ion and the escape fraction are. We just go straight to the ionizing output. We apply this at redshift 2, and then we do this at redshift 7 with JWST and ELT, and it will be easy. The compact starburst systems that we've been looking at so far are consistent with having data fully support there being multiple bursts of star formation, and these things could be somewhat older, somewhat more pre-enriched with mechanical energy than is obvious just by looking at the ionizing spectrum. That helps the ionizing continuum get out. Getting helium-2 right is hard for me, but that will change. It would be very useful to look bluer into the ionizing continuum if possible, test this covering fraction and covering fraction conclusion from UV absorption line spectroscopy, see if the same thing is observed there. Green peas are starbursts in a low surface brightness galaxy, and we're just picking out the face-on ones that we observe. And I'm happy to be wrong about this. It's just an idea that I'd like to put out there. Balmer lines will underestimate the ionizing continuum output if the dust is distributed in a clumpy geometry, and there's a meeting in Stockholm next year that you should register for. And that's the content of my talk.
And now for some singing. Questions?
Oh, so I'm sorry that I can't ruin your face-on disk thing, but I would just point out that a lot of the green peas that I've looked at are detected in Ys, even though they have
are detected in Ys. Most of them are, right?
Most of them are, even though they have no evidence of dust in their Balmer lines. So there's something else there.
So does that falsify or support his model?
Support, I think.
Score! Come on, you guys know way more about this topic than I do. All right.
Do you think your multiple burst star formation history is realistic for a galaxy at the ionization epoch? Do you think, what is the time scale of your bursts?
Well, the times, they're coming in on the order of 10, 20, 30 mega-years separated. So I think that's not an extended star formation history, that's recent. And I think it's probably, I mean, star formation should coordinate on something like the free fall timescale, and that ends up being a few tens of mega-years as well. So it should be on that order. I think it's completely fine at high redshift.
So this with the helium-2 is really worrying me a bit. Nice O's. Now, what are those?
L2s.
So is there maybe something that all of us are missing? I'm sure you have thought about what could be the reason that everybody fails to reproduce this.
Well, I'm probably failing to reproduce them because it's very hard for everybody to get right. But the reason why my star formation histories end up being so different, I think, is because I'm just using Starburst 99 models. These are ordinary, isolated, massive stars. And probably this would improve if I were to use something more exotic.
Please.
I mean, Elizabeth has told us over and over again that the stellar models don't know how to get the ionizing spectrum right at the energies of helium-2. So it's not surprising to me that we don't see that.
Maybe some of you remember on my talk on Tuesday, I had shown that very hot Wolf-Rayet stars can produce a huge amount of helium ionizing photons. And if these stars are at very low metallicity, their spectrum is otherwise nearly featureless. So you will not see in the unresolved spectrum of your cluster, or so you will not see any noticeable Wolf-Rayet typical emission features like 4686 line.
You see them in the optical, right? You see them in the optical, right? Sorry.
No, the spectra are nearly featureless.
Yeah. Okay.
Yeah, but there are also problems like in Vilch has talked about, in SBS 0335 where they've done, and 1Zuki18, they've done the result stars, they've counted all the Wolf-Rayet stars, and they've added up the energy, and they can't produce the helium-2. They've done the most detailed studies. If you look at the Carrig papers 2015 and 2018, it's like the prime example of not being able to reproduce helium-2. They have the X-rays, they have the stars counted up, and they can't do it. Carolyn Carrig.
Yeah, right.
Can I just mention? There are also theorized and probable through evolution channels dwarf helium, stripped helium stars that would be far ultraviolet sources and would not show up in the wave bands that have been looked at to date. So Ilva Gertberg, Selma de Mink's Amsterdam group have been looking at these in detail, and we think we would predict some of them from BPAS. There might well be even more out there, and I'm not sure any of the surveys to date would have seen them in the optical or the UV work done to date.
Interesting. Okay, can we move on to the next speaker, and please save any further questions for the discussion? So our next speaker is Stefan de Barros. No way. Yeah, of course.
So, I think you can hear me? Okay. So, as I need to leave, I cannot, thank you. Since I need to leave and I cannot wait until you end the conference, which I'm awfully sorry for, but this is the moment where I would like to say a big, big thank you to all of you for coming here, for being here at the conference, and for making this conference such a great success. And I need to tell you that also everyone here at the Academies was very happy to have your conference here. They are all thrilled by each and every one of you. So thanks, a big thanks to Polis Papaderos for organizing it, for the organizing committee. And thanks for the good cooperation we had in organizing everything, every detail, and we really hope you had a great time, and we wish to see you back here at some point. Maybe also somebody else wants to organize a conference here. Don't wait for Polis. He will, but maybe some of you will too. So thanks a lot, and all the best. Well, thank you. You know, this is a two-sided thing. We can only be as good as you are. So you've helped us tremendously do our work, and we hope you were helped by that. So one last point. There are a few names. I don't want to read them now, but I will give them to Polis. There are just a few people who haven't paid yet, so please do that until 5 o'clock today, because some of you are leaving quite early tomorrow morning. So have a good trip back home, and all the best for all of you. Thank you.
Okay, thanks. So I'm Stéphane de Barros. I'm working at the Geneva University in the extragalactic group under the supervision of Pascal Heusch. So most of my slides, in fact, you have already seen everything. So all the story about the leakage of ionizing photons is to try to explain the cosmic ionization. So we have an idea of when it happens, because, for example, from the view of star-forming galaxy, there is a drop of the detected Lyman-Alpha emitters at around Redshift 6, both bright and faint. For the responsible for the cosmic ionization, we have plenty of faint star-forming galaxies and few AGNs. So we know that it's super easy for Lyman continuum photons to escape from AGN, but it seems quite difficult to see them escape from star-forming galaxy. Until recently, we didn't know a lot of them. And it seems that the reionization is patchy. The more bright galaxies are in overdensity, where the faint galaxy contribute to ionize those bubbles, and that's why probably we are able to see few very bright Lyman-Alpha emitters at redshift higher than 6. So I'm going to talk about the diagnostics. You already saw that too. So there are two main framework to explain how ionizing photon escape: through holes, where basically there is nothing, and or you can add dust. I'm not going to talk about dust there, but you have holes where the ionizing photon can escape directly, or you have a density-bounded nebula, so basically everything is ionized. So in this framework, you can use the low ionization metal lines, the UV lines, to derive the covering fraction. So if the covering fraction is non-unity, you can have Lyman continuum photon escaping. And in this framework, the O3 to O2 ratio is sensitive to the escape fraction. But the point is that the O3 to O2 ratio is much less sensitive to the escape fraction than other parameters like the metallicity or the ionization parameter. I think it's very difficult to directly link the O3 to O2 ratio to the escape of ionizing photons. And another point, with those two pictures, there is no reason that these two diagnostics are linked. Another thing is that if you have holes, or in the case of a density-bounded nebula, the Lyman-Alpha profile predicted are completely different. In the case of a density-bounded nebula, you expect a classical double-peaked Lyman-Alpha profile, and the velocity separation is going to give you the column density, the neutral hydrogen column density of crossed by Lyman-Alpha photons. If you have holes, basically the Lyman-Alpha photon is going to peak at the systemic redshift. So in this case, basically, you will have in theory, you don't have any possible diagnostic with nebula line ratio if you have just holes, and you have if you consider the density-bounded nebula. So maybe probably the truth in between. So I'm showing those plots. You already saw them. It's about the largest homogeneous selected sample of Lyman continuum emitters. So it's at redshift 0.3 from Isotov and collaborators. So they had the targeted 11 galaxies, and for now, it's a 100% success rate. From John Chisholm's work, he derives so the covering fraction of those galaxies. It's non-unity. And he also derived the neutral hydrogen column density, and it seems that's way too high to allow ionizing photon to escape. So this result is in favor of holes as the main mean for ionizing photon to escape from galaxies. And if you look at Lyman-Alpha profile, the velocity separation of the peaks observed compared to the theory is way too high to explain the escape of ionizing photons to low column density. Low column density. So it favors also this scenario with holes. And again, the O3 to O2 ratio, so all those galaxies have been selected with a large O3 to O2 ratio, but there is no obvious correlation between the escape fraction and this ratio. But in a previous work by John Chisholm and collaborators, it seems that those galaxies, those leakers, have no special feedback compared to a control sample. So you can ask the question why there are holes in those galaxies and not others. So maybe the geometry of this galaxy plays a role. So why I'm focusing on nebula emission? Because so we want to find diagnostic, but we would like to use them on a high redshift galaxy into the cosmic reionization era. And so they are diagnostic based on Lyman-Alpha, but I already shown this plot. The fraction of Lyman-Alpha emitter at high redshift, at redshift higher than 6, drops quite dramatically. So we are able to detect some Lyman-Alpha emission from bright galaxies, but for now, there is nothing like that for faint galaxies, and we think that the faint galaxies are the main contributor to cosmic reionization. See also the Marco Castellano result about that. So we can try to derive the covering fraction from UV absorption line, but again, it's expensive to get them. You can get them for bright galaxy, but it won't be feasible for faint galaxies. And the same thing for the magnesium-2 line is going to be expensive to get it already from bright galaxies, maybe so infeasible for faint galaxies. So the bottom line here is that the diagnostic that seems to work and are consistent with the framework where ionizing photon escape through holes are not usable at a high redshift at the epoch of the cosmic reionization for galaxies responsible that we think that are responsible for the cosmic reionization. So what I did is made a photoionization grid. So I'm using cloudy with BPAS SEDs as input with different parameters. In fact, I'm trying to keep as many parameters as free as possible. So the metallicity, ionization parameter, age, assuming the constant star formation history, also the carbon to oxygen ratio. I'm basically using the same modeling as in the Beagle code by Chevrelar and collaborators. And I'm also adding varying the column density, the neutral hydrogen column density. So with that, you can make prediction like that in Nakajima collaborators. Or you can interpret observations. So I just show an example of a redshift A dropout with some kind of crazy Iraq color there that you can explain only with some kind of extreme stellar population, few million years, and a very high ionization parameter. So that I'm going to talk about that. Matthew also talked about that. Is that everybody is looking at for ionizing photons near the 912 angstrom. And if you derive then the escape fraction at this precise wavelength with the photoionization cross-section at this wavelength, you get something like that, the relation between the neutral column density and the escape fraction. So here, the escape fraction is the ratio of input ionizing photons to output ionizing photons. And this is an example so of a SED, a typical SED that should be representative of a redshift 8 galaxy. But when you look at what's coming out from cloudy, there are plenty of high energy photons that are able to go through much larger column density than 10 to the usual fiducial value assumed, 10 to the 17.4. So, and that's here. So this line is broad because I'm putting all my models in there. And why it's like that? Because for most models, when you are using BPAS for very young galaxies with low metallicity and high ionization parameter, the number of ionizing photons at longer wavelength compared to the number of ionizing photons at 912 is basically flat. So now there is a second effect. It's the nebula. It's a recombination within the cloud. In fact, many photons that are absorbed within the cloud by the neutral hydrogen recombine, and they are going to repopulate this region there. And so basically, when you detect a galaxy with some flux at this wavelength, it can be ionizing, mostly ionizing photons due to recombination. You can also see the talk by Goran Oslin. And so basically, why there is that and nobody is considering, because most people assume the on-the-spot approximation where the ionizing photons emitted due to recombination are immediately absorbed in the cloud, which is not true, depending on the column density. So the result there is that you can have a column density of 10 to the 18 and still have something like 10% escape fraction. So if you go to higher column density, you will have a smaller fraction, so you can go up to 10 to the 18, almost 10 to the 19, you have something like 1% escape fraction, but this effect is going to disappear. It's the only photons that are going through are the very high, very energetic photons. So just considering this relation and taking the column density derived in the last Steidl paper with this sample, so those column density are very uncertain because they derive the column density from the Lyman wings, and basically they don't see them. But if you consider those values compared to what the expected escape fraction just at 912, you see that the escape fraction is much higher than derived with the fiducial value. You can go up to from 10 to the 70%. So there, even if you find a low covering fraction, non-unity covering fraction, many ionizing photons can escape through the neutral hydrogen present in those galaxies. So now nebula diagnostic, I'm using a high chemistry approach with my grid of photoionization. So basically, I'm trying to fit all the line ratio of an observed galaxy with my photoionization grid. So first, I started with the largest sample, the local leakers. And I found that one line is very sensitive to the hydrogen column density. It's a 0.16300 angstrom. And as you can see, so in blue, it's what you see through a column density of 10 to the 18. And in gray, it's what you see with no leakage at all. And you see that this line is strongly depleted when you start to decrease the column density. So I found a diagnostic. I found that the leakers, local leakers with this line detected, I can derive the column density directly from the nebula emission. And that's what I found. I compare, so for, there are in the Simon Gazani work, there is, and the collaborators, there is 5 of those leakers. There are 5 local leakers, and 3 of them have this line detected. And that's my estimation of the column density based only on nebular lines. So compared to the estimation based on Lyman series absorption and based on the O1 absorption line. And you can see that the values are quite almost on the one-to-one relation. So the point is that my conclusion for the local leaker is consistent with the Simon Gazani and John Chisholm results. The column density for those galaxies is too high to allow ionizing photon to escape, even taking into account recombination or very highly energetic photons. But the point is that I'm also fitting the O3, O2, O2 ratio of those objects. So in fact, those objects that have been selected through large O3 to O2 ratio, it seems that the O3 to O2 ratio has nothing to do with density-bounded nebula and the leakage of ionizing photons. So there is no direct link. Maybe you can find an indirect link, but it seems it has nothing to do with density-bounded nebula. And so, in fact, since I can use my diagnostic for all the leakers with 01 6300 detected, which is more galaxies than they were studying in the Simon-Gazan paper, I did the same work for all of them with this line detected, and all of them fall at neutral hydrogen column density higher than 10 to the 19. So it seems that most, or the large fraction of the local leakers, the ionizing photons are all escaping through holes. There is nothing to do with density-bounded nebula condition. So, as I said, we are trying to find diagnostic to apply them to the cosmic ray ionization era. So I am now showing something that, in fact, a galaxy that is a redshift 3.2, so it's ion 2, a local leaker, high redshift leaker, found by Van Zelle and collaborators. And in fact, this galaxy, the data that we have about this galaxy it looks like what we are going to get with GWST for redshift 6, 7, 8 galaxies. And if I try to do the same thing, fit all the line ratio at once with my photoionization grid, I don't get any constraint on the column density. So for now, we can't say anything yet. There is an ex-shooter observation ongoing, so maybe we hope that we are going to have stronger constraint on some lines, and this is going to help. And so that's my summary. So not all diagnostics are consistent. Everybody is talking about Lyman-Alpha profile, O3 to O2 ratio, absorption lines. But if you take simple frameworks, so you can use the Lyman-Alpha profile of the local leakers, for example, is not consistent with holes. Another thing is that high neutral hydrogen column density can allow ionizing photon to escape. You can go up to 10 to the 19 and have an escape fraction of 1%. It's possible to derive directly the neutral hydrogen column density from nebular lines, but it's quite a faint line, 016300, which is detected in most of the local leakers. And my results are consistent regarding the neutral column density with Simon-Gazan and John Chisholm results. And the bottom line there is, since I fit all the line ratio, I find that the O3 to O2 ratio has no direct link with the leakage of ionizing photons for the local leakers. That's it.
So we have time for one or two quick questions. Right. So can you explain the physics underlying the sensitivity of O1 to the total recombination rate?
So it has the same ionization.
Right.
The first ionization energy is very similar to I.
That's right.
That's right.
It's just that simple.
Yeah.
Oh. Thank you. Okay.
I guess just kind of related to that, I was wondering, you don't expect to see a lot of O1 at high ionization, and the leakers are fairly high ionization, right? Like, the ionization curves show more O1, I guess, for about log 2 less than log U less than -2. Is that like tied into your models of the O1?
So in my models, I'm varying the ionization parameter from -1 to -4. So that's taken into account.
And it agrees like with what they measure for the leakers?
Yep.
Okay.
So let's thank Stefan again. And our next speaker will be Gerhard Ensler, who is going to talk about Lyman Continuum and something else.
Not only. Where's the HDMI? I need an HDMI cable, which was here. Ah, here it is, okay. Yeah. So now you saw the talk already. Okay, I will talk about photoionization calculations, which we have performed by applying, for instance, codes to some models. And these are my collaborators. I will talk about one part that is already published and the new part which is now under submission. The motivation was a little bit at a lower level because we know, for instance, for dwarf galaxies, analysis of the star formation rate, or for instance also of the metallicity or so, they depend strongly on assumptions. And the assumptions, for instance, are that we can derive the star formation rate, for instance, from H alpha, that we can derive metallicities from line ratios, oxygen 3 and oxygen 2, and in addition also that the H2 regions, for instance, are homogeneous and have the same temperature. This means not allowing temperature fluctuations because that complicates the whole analysis. So our question was first, for instance, how reliable are the analysis programs or the analysis at all? And if you apply this, for instance, already to observations, you do not know, for instance, what is the real state of the dwarf galaxies, of the dwarf galaxy you try, or of the galaxy at all, you try to analyze. So the best is to take a model where you know all the conditions. This means you know temperature, you know the radiation field, you know the densities and also the ionization stages of the interstellar medium, and to apply this, apply now the analysis code to such a model. And then find out whether the model, for instance, reproduces the state of the what you wish to derive the results, let's say, for instance, of the star formation rate. So we try really to study a well-known model, and this model was taken from a bunch of models which we performed, but at that time the aim for these models were to understand, for instance, under which conditions galactic winds, for instance, are produced in dwarf galaxies, and how is the metallicity, for instance, reacting to these strong galactic winds. But we took out one model, that is this one, which is a flat H1 distribution in the galaxy of the gaseous disk with star formation, which is self-regulated and by this self-consistently applied, and in addition also 10 to the 8 solar masses in baryons. This means with a dark matter halo of a factor of 10 approximately more. This galaxy was then, for instance, that is at a stage of 140 mega-years after we started the model. The star formation rate is approximately, because it's self-regulated, is approximately constant, so we do not deal with a starburst. And we see already after 140 mega-years that a large plume of hot gas is expanding vertically out of the galactic disk, and we have divided the different sectors, for instance, under particular aspect angles into 12 of these sectors. Sector 1, for instance, is in the equatorial plane, as you look, for instance, edge on to the galaxy, and the other one, sector 20, is directly pole on to the galaxy. And then we can, for instance, consider how the aspect angle, for instance, also changes the results and the diagnostics, and what is in total then, for instance, the average, or this means the average, but the total flux in different lines, and also, let's say, in H alpha, and what is the assumption for the whole galaxy then. The stellar radiation field is taken also from starburst 99, as you see here, but in addition, and that is let's say the progress also in these models, is that we have to take the radiation from the hot bubble also into account. So we add to the radiation field of the stellar component also the hot component. This means the bubble component, which has approximately a temperature of 10 to the 6 degrees. And what you see here is, for instance, what really comes out of the galaxy, what is emitted from the galaxy. We have a lot of absorption that is pretty clear in the Lyman continuum range, where metals and also hydrogen can absorb, or here are mainly the metals, but a huge amount of photons in the hard Lyman continuum range remains totally unaffected. So that can really leave the galaxy in total. I don't know, I have to show you another important point here. We deal with, here for instance, it's very faint here. We deal with two, we have, for instance, the expansion of the superbubble shifts the surrounding material and forms shock front. And depending on the numerical simulation, the shock front is, for instance, steeper or is a little bit fainter. So we dealt with two models here. The one has this very let's say low increase, this means not really a jump, it's not a shock front, but the low increase in the density to the surrounding. And another model, for instance, has this steep wall of hydrogen which swept up material, for instance, is compiled. And that has pretty clear issues, for instance, and consequences for the Lyman continuum radiation. The hard Lyman continuum radiation can, for instance, penetrate easier than the soft Lyman continuum radiation, but it depends on the thickness of the shell. And here in the upper part, we have, for instance, the smooth shell. This means the smooth increase of the density. And what you see here is, for instance, that this is this red line that is the oxygen singly ionized, and the green line is the oxygen double ionized. And this means if we, for instance, consider in that range, for instance, we consider the ratio of the oxygen 3 to the oxygen 2 lines, we really achieve a factor of 10 and more. Because the hot radiation from the, or this means the energetic radiation from the hot bubble really ionizes the oxygen much stronger than the pure stellar radiation would do. In the lower part, there is this thick shell. Also, here we have normal conditions, for instance. We have only in the inner part the oxygen doubly ionized also is available, but then it drops down because of the consumption of photons already in the shell itself. And oxygen singly ionized, for instance, increases, and in the outer part, so we get a mixture of oxygen 3 over oxygen 2, but never these high ratios of a factor of 10. The same holds also for the silicon for the sulfur lines and also for the nitrogen lines. This means we get, for the low ionization stages, we get really low intensities or equivalent widths from these metal lines, singly ionized metal lines. One important point in this paper was, for instance, to consider whether the H-alpha flux really tells us the star formation rate. You all know about the Kennicutt law to derive from H-alpha flux the star formation rate, and we have done, for instance, this. We derived the star formation rate for our model with respect to the star formation rate which we know from the model. We know what is the star formation rate in the model, and due to the expansion of the bubble, this ratio, this means it's mainly the H-alpha emission, changes. The changes from the normal or from the star formation rate, which is realistic in our model, to an increase by a factor of 1.6, not very dramatical, but it is still significant, for instance, for the determination of the star formation rate. But later, and that was surprising for us, later it drops down again. And the reason is that Lyman continuum photons escape out of the whole galaxy, and this means the difference in the star formation rates goes down again. But this cannot, should emphasize this, it cannot, for instance, explain the difference of the star formation rates derived from H-alpha and UV, which was found, for instance, by Janice Lee and published in 2009. A point that is important for us here, for our conference here, is what is the leakage of the Lyman continuum photons. And the leakage of the Lyman continuum photons depends, it's pretty clear, depends on the aspect angle, what I mentioned already. If you look in the equatorial plane, a lot of Lyman continuum photons are consumed in the shell of the hot wind bubble. But if you look pole on to the galaxy, it depends on, and that is, for instance, visible here. I have to look here. That is visible with these dots here. We look pole on directly in the hot bubble, and the Lyman continuum photons can escape easily there. And on average, for instance, we get this curve here with the thick dots, which are approximately varying from 30% to 60%. So it's really a huge amount of Lyman continuum photons, but one should be careful. These are mainly the hot or the energetic high Lyman continuum photons that might not contribute to the, or cannot contribute, for instance, to the ionization of the surrounding, the environment of the dwarf galaxy. But if you consider this in the epoch of reionization, because of the expansion of the universe and the redshift of these hard photons to softer photons, also it would also contribute. If you go to redshifts between 10 and go down to redshift of 4, these photons are still available and should be able to ionize intergalactic medium. A new study, for instance, also includes the Lyman-Alpha and also, for instance, the dependence on the dust content in these galaxies. The Lyman-Alpha emission, for instance, is visible here in the different zones. Again, the red one is the equatorial plane, and the what is it, purple one also is pole on. You would expect that pole on the Lyman-Alpha should be also reduced because of the bubble, of the expansion of the bubble. But there's on top of the bubble also, there's also the accumulation of some gas, so that the Lyman-Alpha radiation has also, for instance, a contribution even if we look into the bubble itself. And the others, for instance, in other directions, this changes also, and one should emphasize it depends on, obviously, on the aspect angle, and also it changes with time. This means according to the time of the temporal evolution of such a galaxy, you get different values for what you consider. Here on the left-hand side, in this lower figure, we have, for instance, included dust. This one is, for instance, for dust content that is pretty high, that is solar dust content, or this means Milky Way dust content, and that is approximately 1/6 of the dust content. We include this in the cloudy code, and we get, for instance, also for the Lyman-Alpha, we get these differences, for instance, and that is here more than 1 order of magnitude difference, and it obviously depends on the dust content. On the other hand, because dwarf galaxies have only a low content of dust, the effect is not very strong, or should not be very strong, but there are also in the central parts, usually where if starburst or star formation continues, also in dwarf galaxies, there is a significant dust content, and that changes, for instance, also the Lyman-Alpha emission and should be taken into account. So my conclusions. So to be in time, I say it's the first time that I really keep in time. The conclusions here are the following, that dwarf galaxies, for instance, change during the evolution. They change pretty clearly. They change the constitution of the interstellar medium. Star formation, for instance, occurs, hot gas is produced, and that has to be taken into account at which state, for instance, we consider and observe the galaxies. Then we can, for instance, reproduce these very high oxygen 3 to oxygen 2 ratios, and our opinion is that it only stems from the additional Lyman continuum radiation from a hot bubble. That should be taken into account for all the analyses. The high Lyman escape fraction, for instance, of on average 40% or so, is mainly contributed by hard photons, so they will not affect the intergalactic or the circumgalactic medium that strongly, but it can, for instance, been reprocessed to some extent, but on the other hand also for the reionization epoch or so, it should be really an important contribution. This means, in addition to AGNs, dwarf galaxies should be a clear contributor to the reionization phase of the universe. On the other hand, and that is something that is also important, we do not know what is the physical state of the dwarf galaxies in this very high redshift ranges. It's not clear whether they boost, for instance, in their star formation, or whether they start smoothly with the star formation and do not contribute that much. The Lyman-Alpha emission strongly also depends on the aspect angle, that is pretty clear, but I think the underline is all the time that we have to take the hot gas and the radiation of the hot gas phase also into account for the analysis of these galaxies. Thank you.
Some questions? Don't be shy. I actually have one. So you said that you end up with low N2 and sulfur 2 strengths. So if you put that gas on a BPT diagram, what would it look like?
It would be really in the lower end. If you take the BP diagram and you take these, what is it, sulfur as compared to or
H alpha
by H alpha,
yes.
We would be at the lower end.
Where the stars are.
I would say lower than the normal H2 regions.
So even more extreme.
No, that would we would shift it to the left corner.
But wouldn't then O3 be strong relative to H beta, and then wouldn't it shoot it up?
That shoot it up, yeah.
So it would end up.
Yeah, you're right. Yeah. H beta is on the.
Yeah. Okay. Fascinating.
Thank you for the talk. I have a question. Do you have can you estimate the X-ray flux from these lattice bubbles? Because there are observations, and Mineo, they have this diffuse X-ray component in galaxies, so maybe you can make an X-ray luminosity function or some predictions for that?
We could do, yeah. We can do, yeah. Let me only show you, because we go really in a high energy range here. You see, we reach we reach 1 keV, and that is already in the range. That means between 0.1 and 1 keV, you're in the normal range of Chandra and XMM.
Yeah, in soft X-ray.
Yeah, soft X-ray part. Yeah.
Mm-hmm. Is there another question? If not, let's thank Gerhard again. And now for the ultimate talk and the ultimate session. So it's game point, match point. It's Yoki Rosedal, and he's going to talk about something to do with Lyman Continuum.
All right, thanks, Matt. Thanks to the organizers for allowing me to be here. Thanks to the rest of you for sticking with me. So I'm going to talk about, as requested, I'm going to talk about, kind of give a review of simulations in the last decade about escape fractions and cosmological simulations of reionization. And then when I'm done with that, I'm gonna talk a bit about what we've been doing in Lyon with the Sphinx simulations of reionization for the last couple of years. One of those is running here in the background. You can see reionization happening live. Okay, so galaxy formation is you can view it as a really big loop. So on intergalactic scales, the dark matter collapses into a cosmological web of sheets, filaments, and halos. The baryon gas cools inside those halos into galaxies, collapses into molecular clouds, form stars. The stars then emit winds, radiation, supernovae back into their surrounding, disperse those clouds, coalesce to form galactic winds that enrich the intergalactic medium and the circumgalactic medium with metals and radiation. And then the loop is closed as this enriched intergalactic gas accretes back onto galaxies, forming subsequent generations of stars. To tackle this nonlinear, multi-scale, multi-dimensional problem, theoretically, you need to go to simulations. And if you want to study escape fractions and reionization, you need to run radiation hydrodynamical simulations. So there's been a lot of interest, of course, in reionization simulations over the last couple of decades. They can be split more or less into two classes of simulations. So on one side, you have large volume simulations that capture a large sample of galaxies in a volume where you aim to cover basically a cosmological homogeneity, so tens, even hundreds of megaparsec. But in having such a big box, you sacrifice in resolution. So there's no way that you can resolve the escape of radiation inside galaxies. You can't really even resolve the low mass halos that everyone is predicting that reionize the universe. So in order to do that, to understand what's going on inside galaxies, we need to go to different kinds of simulations. We need to have very small volumes, and we use a so-called zoom technique. So I'm showing that here. You basically run a cosmological volume, which is already kind of small, and then you allow you focus the resolution on a halo or two that you target within that volume. So here you can see that there's a relatively high resolution at the center, and if you go outside, the resolution is very small, very low. So you don't have to spend a lot of computation on that intergalactic medium, which is only there for the gravity. So you can predict the escape of ionizing radiation from galaxies like that with good enough resolution, but you can't really capture the full reionization process since you only have one galaxy and its satellites forming inside the box. So going back about 10 years, Nick Nedden is really a pioneer in all kinds of reionization simulations. He put out this work in 2007, where he ran a cosmological zoom simulation, much like I was showing in the slide before, targeting a halo about a few times 10 to the 11 solar masses and its satellites. And then he measured the escape fraction of ionizing radiation from stars forming in that galaxy. The resolution, by the way, is actually pretty good for these days, 40 parsec. And here are the results. So you can focus on the black squares. These are escape fractions of ionizing radiation for the main halo and the satellite halos. And they're all very low. So they're super low escape fractions, on the order of a few % at most. And around the same time, other people seem to be finding very similar results. They basically were all getting tiny escape fractions. And you should actually notice in this slide what the gas disk looks like. It looks very smooth and solid. It's basically absorbing all the radiation which is being produced inside that disk. And all the radiation which is escaping away from the disk is in these stars, which you can see here in yellow, which for some reason have managed to get outside of the disk. And the radiation from those, of course, can get into the intergalactic medium. Then a couple of years later, John Wise, he wrote a code to do radiation hydrodynamics, Enzo Moray, I think it's called. And he ran a series of collapsing halo simulations with super high resolution, actually incredibly high resolution, which look like that. These are three of the halos at different times. And all of a sudden, he's getting huge escape fractions. You can see here, I think the red diamonds here correspond to the halos that you're seeing here. These correspond to slightly different simulations, but the point is all the escape fractions basically are huge. It's on the order of 20 to 80%. Then the following couple of years, there's plenty of work on measuring escape fractions in simulations, and there is just all of a sudden this wild disagreement between what people are getting. Some are getting high escape fractions, some are getting low escape fractions. Some are getting higher escape fractions with higher halo mass, some are getting the opposite, It's just everywhere. And there's no obvious reason really why they are so different. There are many things, of course, that are different, and there are probably many reasons. But the general trend that you can kind of see in those papers is that if you look at the papers with low escape fractions, you have these kind of disks that are kind of settled. The gas is all in one place. It's surrounding the stars which are emitting the ionizing radiation. In the simulations where you have high escape fractions, everything is a mess. And probably, they don't all really say, but what it looks like is that these simulations, they all have a very strong feedback going on, and these, they don't. And the strong feedback is really what seems to be allowing the radiation to get out. It's carving the holes into the interstellar medium. So that's indeed a theme that kind of came out of those papers. So a few years later, there were these works which all kind of agree that it is really feedback which is regulating the escape of ionizing radiation from stars. So I want to just highlight one of those works, which is by Maxime, who unfortunately had to leave. I think he showed this image already in his talk on Wednesday. In a 2017 paper, he was a postdoc in Lyon, by the way. He ran a series of 3 cosmological zoom simulations with about 10 parsec resolution. So you can see here one of the most massive halo in the gas and in the stars. And then he looked at the escape. So these are radiation hydrodynamical simulations, by the way. And he post-processed them by looking at the fraction of photons produced within the galaxy which escape beyond the virial radius. So this plot here shows in blue, you see the star formation rate in the galaxy. In orange, you see the rate of outflowing gas beyond the virial radius. And in red, you see the escape fraction, right? So there's definitely, things are not very settled here. Typically, the galaxy is kind of passively evolving, and there's not much happening. There's not much star formation. There is 0 escape fraction. Then you get a burst of star formation, and this is kind of immediately a few million years later, followed by a burst in outflow, which is generated by the supernova explosions coming from that star formation. And at the same time, you have a peak in the escape fraction. So what's going on here is that stars are forming in a very dense gas, which has kind of collapsed or accreted onto the galaxy. About 3 million years later, the stars go supernovae. That kind of disperses the environment around those young stars, and then suddenly you get a peak in the star formation in the escape fraction. It's only a peak. It only lasts for a very short time, a relatively short time, because you just disperse the gas, so you can't form stars anymore in that environment. You shut down star formation. So the gas kind of comes back. The galaxy becomes dim, and at the same time, the escape fraction goes down. Okay. Then there was another exciting development around the same time, which has to do with binary stars. There was a paper by the FIRE people. You probably all know the FIRE simulations. They basically post-processed 3 of their FIRE simulations. So these are again zoom simulations. Not radiation hydrodynamical, but they can still trace rays from the stellar populations which are formed inside the galaxies. So they can post-process kind of an estimate of escape fractions from those galaxies. So first they did that with, I believe, Starburst 99, and they put out a paper saying we get depressingly low escape fractions. And then in this paper, a follow-up paper, they did the same thing, but they did it with BPAS instead of Starburst 99. Without and with binary stars included. So you can download BPAS on the web, you can just couple it to the post-processing, you can get luminosities, ionizing luminosities as a function of population age and metallicity. And in doing so, they got this very cool result that with single stars only, you get these white diamonds, which are averages over the last 100 million years, I think. You get, pretty low escape fractions, few percent. And if you put in binary stars, you boost the escape fractions by a factor, I think it was 4 to 6 or something like that. So you get a very, very significant increase in the escape fraction. And it actually becomes on the order of 20%, which is what everyone thinks is needed to reionize the universe. So it looks almost too perfect. So to explain kind of what's going on, it's basically the same explanation that I just gave you in words. The stars are forming in a dense cloud. You have to wait for about 3 million years until the stars start to explode. The most massive stars start to explode. The cloud gets dispersed. So it's only after about 3 million years or so after the birth of the stellar population that you get the radiation escaping at all from the stars. So if you put that into the context of the luminosity as a function of stellar population age, here shown for, this is Bruzel and Charlot, that's another spectral energy distribution model for stellar populations, and BPAS. So just focus on the solid lines, that's the low metallicity, which is really relevant for the high redshift reionization era. So in the beginning, the luminosity is more or less the same for both sets. And it's only after about 3 million years that they start to differ a lot. So here the BPAS model is giving much higher luminosities. I mean, they're still lower than they were in the first 3 million years, but they are much higher than for the single star populations. But we actually don't really care about the first 3 million years because that's the time when the stars are embedded in a dense, optically thick environment. And it's really only here that it starts to matter what kind of luminosity you have. So that's kind of the explanation why it matters so much to have the binary stars, why you get so much more escape of radiation when you have binary stars compared to single stars only. So that kind of brings us to the swing simulations because we are partly using the swing simulations to study the effect of using binary stars instead of single stars only on reionization. So now to bring up this schematic again of the two classes of simulations that people have been doing. With swings, we're trying to merge these two classes of simulations. So we're trying to have a representative-ish volume, cosmological volume, and at the same time have high enough resolution that we can start predicting the escape of ionizing radiation from every galaxy within that volume. So we can predict the FS, and at the same time we can predict the reionization history of that box. So here are the simulations in context with other reionization simulations in the literature that have been performed in the last 10 to 20 years. I'm not showing these tiny volumes. I'm only showing simulations that actually model reionization here. So this is a plane of a physical resolution and volume. So like I told you, when people do reionization simulations, they try to go for large volumes. You know, they aim for this scale here, roughly. But in doing so, they have to make sacrifices in the resolution. So they are very, very far from resolving the large star-forming clouds. So now we're kind of doing the opposite. We're trying to gain in resolution, and instead we're making a bit of sacrifice in terms of the volume size, right? So we have 10 parsec physical resolution. We start to resolve things going on in the ISM of galaxies. But our volume is only 10 co-moving megaparsec so far. Hopefully we'll get time to run larger volumes with more galaxies. There are many goals to the project, and we're only tackling a few of those goals yet. Maybe in the next meeting I can present more. We want to understand the sources of reionization, for example, which mass galaxies are dominating the production of escaping ionizing photons. Obviously, we want to model the Lyman-Alpha signatures of these galaxies using the Raskas code that Jeremy was presenting yesterday. And we wanted to look at the contribution from binary stars to the reionization process. Now, not just looking at the escape fractions, but actually looking at the evolution of the neutral fraction of the volume that we're simulating. So just to say a few words about the code that we use. So the base is the Ramses code, which is a well-known and very widely used cosmological code. If you're in France, that's the code that you use. During my PhD and my postdoc years after, I worked on implementing radiation hydrodynamics inside the Ramses code. So solving this radiative transfer equation on top of the hydrodynamics. So solving just this is the evolution of the beam intensity as a function of advection, absorption along the line of sight, and emission from stars, even from gas. So this is a very expensive problem to solve on top of the hydrodynamics due to the high number of dimensions and in part due to the tiny timescales which are involved, which is because of the speed of light of the radiation. To get around these problems, well, first of all, we reduce the speed of light, which allows the simulations to be much faster than they would be with full speed of light. And the other thing we do is we use the so-called moment method to get rid of the angular dimensions in the radiative transfer equation. So it basically means that you treat the radiation like a liquid instead of treating it like a fluid. And that has a very, very nice advantage, which is that you can have an unlimited number of sources of radiation in your simulation. So this is a rotating galaxy disk. It's just the radiation flux that you're looking at. And there are hundreds of thousands of radiation sources, and it's just as expensive or cheap, depending on how you look at it, as having one source of radiation with that method. And that's very important if you're doing a cosmological simulation of reionization, because you want to have many, many, many sources of radiation. So it's all coupled to the hydrodynamics. So photons are just emitted from stellar populations on the fly. You can even emit photons from recombinations in the gas if you want to. And then they propagate through the volume, and then they interact with the gas by ionizing it, and even you put in the momentum from the photons to the gas as well. And just to advertise, it's a public code. It's totally all just a part of Ramses, and you can download it and run simulations. So we run two kind of main volumes with the swing simulations. A larger volume, which is 10 co-moving megaparsec in width, and then a smaller volume. So this is 8 times smaller volume with the added gain that you have higher resolution in that simulation. So the purpose of this one is really to go down to the atomic cooling limit of halos, roughly 10 to the 7 solar masses. So to capture all halos that potentially can be forming stars in the universe. A few words about the setup of the simulations. 10 parsec resolution, the mass resolution is a few times 10 to the 4 solar masses per dark matter particle. We form stars out of gas. Each star represents a stellar population of 10 to the 3 solar masses. We use a star formation model which is very comparable to what people are using in fire, for example. The important thing about it is that it leads to very bursty star formation, as opposed to have nice, smooth star formation over the disk. This actually enhances feedback in galaxies. And then we inject supernova explosions with momentum kicks. That's another subgrid model that we put in there. But it turned out that we needed to play a bit with the supernova feedback. We needed to boost the rate of supernova explosions to reproduce something that looks like realistic galaxies in observations. So I'll come back to that a little bit later. We don't do any calibration on the unresolved escape of ionizing radiation from stars. We just put in the luminosities given age and metallicity from BPAS and from Bruzel and Charlotte, and compare the two. So these are the halos that we get at Redshift 6 in our 2 volumes, so 10 and 5 megaparsec volume. The most massive halos are not very massive. That's because our volume is pretty small, right? However, we can resolve halos in this smaller volume down to this roughly 10 to the 7 solar masses. Because the box is very small, it's kind of dangerous because you're really affected by cosmic variance, right? It's nowhere near the cosmological homogeneity scale. So what we needed to do to minimize the effects of cosmic variance, we ran a lot of simulations, a lot of dark matter only simulations to Redshift 6. I think it was 60 of them. And then we took kind of an average halo mass function from those 60 simulations and picked the one that gave us the best average halo mass function at the 3 different redshifts. So this is to kind of minimize the effect of cosmic variance, to not have too many massive halos, to not have too few or too many low mass halos. And then we ran the simulation with what we thought was the best initial conditions. And with the boosted feedback that I talked to you about before. And we get a luminosity function. So this is really what we need to get to start getting predicting a realistic reionization history. So this is a Redshift 6, and the different lines here are just the different volumes. So 5 megaparsec is thin, 10 megaparsec is thick, and red and blue are the single and binary stars. So they're all pretty much the same. And they agree fairly well with observations at high redshift of the luminosity function. So that's good. That means that we have roughly the correct amount of intrinsic ionizing luminosities per volume in our volume. Then just to move a quick movie of the simulation. So this is the 10 co-moving megaparsec box. You see here the full volume in gas density, temperature. Jeremy was showing a similar movie the other day. Blue is just very cold gas. White corresponds to 10 to the 4 Kelvin, so gas which has been heated by photoionization. And red is galactic winds generated by supernovae. So you see the box is starting to reionize fairly early here. This is with binary stars, by the way. And here you see kind of a zoom in on the most massive halo in the simulation. Again, gas density, and here ionizing radiation flux. So you can see this breathing scenario that's going on in here in the galaxy. What happens is the gas kind of falls into the gravitational potential, becomes very dense, it forms stars. After a few million years, the stars explode, and they just completely blow away the interstellar medium around those stars. And at the same time, you get a huge flash of radiation which escapes away from the galaxy. And then the gas starts to fall back again, and you get, again, the same thing happening again and again. And you can see here now towards redshift 6 that the volume has been pretty efficiently reionized. The full intergalactic medium is hot. So here is then the volume-weighted neutral fraction evolution with redshift, comparing now binary stars and single stars. So these are exactly the same simulations. The only difference is the luminosities of the stellar population as a function of age and metallicity. One with single stars, Brazil and Charlot, and one with binary stars. And there's a huge difference. We barely managed to reionize the box with the single stars, both in the small and the large volumes. And in both the large and the small volumes, we really ionized the box, actually a little bit prematurely with binary stars. So this difference, this fact that you have higher luminosities later on in the evolution of the stellar population really makes a huge difference in the reionization, in the amount of photons that get into the intergalactic medium. How much time do I have, by the way? 6 minutes? Okay, that's probably fine. So here we look at the escape fractions, now focusing just on one halo. So this is the most massive halo in the smaller volume that we have. So here you can actually see the mass evolution of the halo and the stars in that halo. So the plot here shows it's a bit messy. It shows in thick, you see the escape of ionizing radiation beyond the virial radius of the halo, in blue with binaries, in red with singles. And the thin lines are the corresponding luminosities, so the intrinsic ionizing luminosities of that galaxy. So, like I said, it's a bit messy. We see more or less what we saw from Maxime Trebuch's paper. The escape fractions, they really wiggle up and down, and they seem to be connected to starbursts, of course. But it's a bit hard to compare directly, the escape fractions between binaries and singles in that case. So what's going on here is again, just this scenario that I described to you. This is just a few pictures to really kick that message home. So the stars you can see here are in red. So these are young stars, less than 20 million years old. This is the column density of neutral gas, and this is the flux of ionizing radiation. So in the beginning, you have gas, coming into the center of the galaxy. It's very dense, and stars are forming, but the radiation is not very efficiently getting out of that galaxy because of all that gas. So the escape fraction you can see is quite low, even though the luminosity is very high. So then a few million years later, you've started to have supernova explosions, and they have really dispersed away a lot of the interstellar medium. So now you have huge gaps for the radiation to get out. So the escape fraction has become very high. But however, at the same time, the luminosity is now starting to go down, because as you disperse the gas, you're stopping star formation. And then a few million years later, the gas is really starting to come back because there's no more feedback going on in that spot. There are no young stars anymore because of that. The escape fraction is actually still quite high, but it's just that the luminosity now is very low, so there's almost no radiation getting out into the intergalactic medium.
This is just to show the probability distribution of escape fractions. I think that's a bit interesting. If we look at one halo, we've selected here one halo which happens to be a leaker. It's leaking ionizing radiation. And if you look at the distribution of escape fractions, it's just per photon here, you find this kind of a bimodality that you see here in the blue curve. So it peaks, of course, at 0. These are just photons which are not getting anywhere. And then it peaks at about 35%. So it seems that the stars which have escaping radiation, they all seem to be more or less in the same spot. So they all see the same opening angle for the radiation to escape. And then if you just collect together all the galaxies in your volume, so that's all the other curves, that translates into this kind of multimodal distribution. So each hill in this distribution just represents one leaker in the cosmological volume. So you can actually just count the number of leakers in your volume by looking at that distribution. So here's a comparison for the full volume of the escape fractions. So these are in blue here you see instantaneous escape fractions as a function of time for binaries and for singles. And the dashed lines here show the average over the last 100 million years. And again, these are just luminosity densities for the intrinsic ionizing radiation. And indeed, much like Ma et al. Were finding, the escape fractions are a factor of a few higher with binary stars than with single stars. So we basically just agree with those guys. This was for the 10 megaparsec volume. It's a bit interesting to look at the smaller volume. This is the 5 co-moving megaparsec. And if you compare the two, you find that the escape fractions are actually significantly higher in the smaller volume. And that probably means that the escape fractions, you're getting more escape from the low mass halos, because the smaller volume does not have as massive halos as the larger one. And indeed, here we compare the escape of luminosity binned by halo mass. So it's very noisy data. We only have a few hundred star-forming halos in our simulation. So what we need to do is to get rid of a lot of the noise is to stack snapshots over time. So from Redshift 9 to Redshift 6. So these are about 100 snapshots. And if we do that, we can measure sort of the escape fractions given a halo mass. And it's actually surprisingly flat. This maybe not being noise. But you also see that there is a strong decline at the highest halo masses. It's probably real, but it's kind of still hard to say because there are really only a handful. There are probably 4 or 5 halos at this mass and really at the end, towards the end of the simulation. So there's an indication that the escape fractions are lower for the highest mass galaxies, but we can't really be sure yet until we get the computing time to run larger volumes. And here it's also interesting to see that about 70% of the escaping ionizing luminosity is done by these sort of intermediate mass galaxies. These are the galaxies that seem to be dominating the reionization process in our simulations. It's also nice to look at the age of stellar populations which are dominating reionization. Age versus the escape fraction. So you can see that the escape fraction really it's really tiny until like a few million years. And then it goes up significantly and stays pretty high for the next 100 million years or so. And that means that the escaping luminosity is really tiny as well for the first 3 million years, even though the intrinsic luminosity is really high. It's almost half of the total luminosity. You get about 90% of the ionizing luminosity from about 3 million years to 20 million years. And that's, again, because of what's happening in the binary stars. 3 minutes, you said? So I can talk a little bit about the calibration that we needed to do for the feedback. I'm so sorry for keeping you guys here. I almost want to stop talking, but not quite. So we also ran simulations with uncalibrated feedback. So just the rate of supernova explosions as given to us by a Krupa initial mass function. And if we run that simulation, we get a luminosity function which looks like this. So the luminosities are way too high. We have way too much star formation inside our galaxies. That's of course wrong. We have too much ionizing radiation being produced, but it's still interesting to look at what happens to the reionization history. And surprisingly enough, it's almost the same. So this is again for the binary stars, and this is with the weak feedback, unboosted feedback, and this is with the strong feedback. And we get the same for the single stars. So we get almost the same results, even if we have way too high luminosities in our galaxies. And the explanation for that is, well, the feedback is weak. So it's not as efficient as blowing away the interstellar medium of the galaxies and allowing the radiation to escape away from the galaxies. So indeed, if you compare the luminosities, they're much higher for the weak supernova feedback case. But going in the other direction, the escape fractions are much lower. And somehow, weirdly, that sums up to almost the same amount of photons escaping into the intergalactic medium. And that's it. The message, I think the main message that I'm giving here is just how the escape of ionizing radiation is really regulated. Its feedback frees the photons from galaxies. I think you should stay tuned for more coming from the swing simulations. We've already verified that binary populations make a huge difference for reionization. And there's a lot more to come, so hopefully I get to come to the next meeting. Thank you.
Questions for Yoki? Gerhard.
Yeah. I have two questions. The one is, for instance, you mentioned by yourself that the bursting star formation scenario, so which is coming from the fire description or so, might be a little bit unrealistic. If you balance this by more self-regulation and you will not get these strong outflows, would the result be the same, for instance, for the escape fraction?
Sorry. That's a good question. If you've asked me a few months ago, I would have said no. But there are actually indications that it seems to work as well with less bursty star formation. And I'm really surprised by that. But there are people in Surrey, I think Ilyan Ilyev and his people, they've been running very similar kinds of simulations with the same code, but using a different star formation recipe. And they seem to be getting the same. I did not expect it.
But yet that's what I would propose, for instance, or recommend, to have a local self-regulation already taken into account. And another question is, for instance...
Sorry, but just to go a bit further into that, so the classical way you form stars, at least the way that we've been forming stars before, is you kind of by hand put in a low efficiency of star formation, which is kind of a way of putting in feedback. You're just manually dampening star formation.
I know, but you switch this on by your genes mass criterion.
Yeah.
And that also, I think, makes these what is it, the bumps also in the star formation rate. And then another question, if I could ask, for instance, I do not see that this filamentary structure also in the interstellar, not in the intergalactic medium, is represented in your bubble expansion. I would expect, for instance, that along the filaments, the mean free path of the Lyman continuum photons is smaller, so you should see more through voids the escape, or this means expansion, and not along the filaments.
Are you talking about the movies or?
About the movies, yeah.
You mean that you're expecting to see more dark filaments in this one here?
Yeah.
Yeah.
The expansion does not run into the filaments also. This means the ionization should be stopped there earlier.
Yes. So the filaments are actually, at least in the beginning, they are partly neutral. So it's absolutely right. There is a bug in the movie script. So what you're actually looking at is a density. It's not density weighted flux, but it's density times the density weighted flux, and that kind of artificially removes the the black filaments. We verified that with like tiny volume simulations where you see the streams. But it's just a bug in the movie making, so we didn't really run the simulations again just to have nicer movies. But yeah, you're absolutely right.
Any other questions? Yeah, please.
I have a very elementary question, I guess. So I don't know anything about simulations. And when you were talking about binaries, it was just interesting for me to know that do you consider different mass ratio and the sum of the sum of mass for these stars, or there is just one type of binaries that you consider for this simulation?
Yeah, I went to the website for BPAS and I downloaded their table and I used it, and that's it. There's no, at least at the time, there were variations in the initial mass function, so a few variations, but and the highest mass, so we cut off the initial mass function. We picked the one that looks the most like a Krupa, but otherwise it's just that you can download. That's future work.
Just to clarify that point, I believe in the model set that was used to run this, we were assuming a flat distribution in mass ratio and a flat distribution in binary period. In the latest models, we have tweaked those a bit, and JJ and I have just been discussing this. We think it's going to move reionization a bit later and put it back on for points. But we're going to have to wait and see until the next generation of these models are run. In the meantime, very good work. Thank you.
Thank you.
There was a question over here somewhere. Yeah, Angela.
I missed at the beginning, but so do you have the interfaces of the medium, or do you have just neutral medium? So do you form a warm and cold medium? So H1 and then a molecular gas and then dust. Do you include all these ingredients?
Not dust, and not molecules. So we track ionized hydrogen and helium in every volume element. But no, we're not at the level of molecules yet. I think we don't really resolve molecule formation very well at this point.
So there is not also enrichment, right?
There is metal enrichment
cooling.
And metal
okay.
cooling, yeah.
Mm-hmm. Okay, thanks.
I have a question. I wonder the increase in the escape fraction when you go to better improved mass resolution in smaller volumes, is that for all the small volumes you had, or is it for, I don't remember, was it just for one of the smaller volumes? I'm just thinking that if you see it in one smaller volume, it might be representative of the global density field, so it might be something in overdense, underdense region, for example.
Well, we applied the same kind of method to minimize the cosmic variance in the small volume. So the main difference should just be that we have not as massive galaxies. And I think, I still won't tell absolutely for sure. But I think this plot kind of explains it, because, well, you have the low escape fractions, the lowest escape fractions are for the most massive halos, and these massive halos, they don't exist in the smaller volume. So I think that's the most likely explanation for the lower overall escape fractions in the smaller volume. Do you want my mic?
Yeah, thanks. So it looked like getting the number of photons out for reionization didn't look like such a critical test, because you basically said other codes can do it when you know they have different things in their model. So what kind of tests do you think would be, and I guess this could be a general question actually, what kind of tests do you think would be more decisive about not only getting this kind of overall intensity right, but also getting it sort of quantitatively right in the galaxies and in the CGM and the thermal properties and et cetera of the gas?
You just mean the overall properties of the galaxy, or just the escape fraction?
Not exactly. Yes, I think you would have to look at say the topology of the galaxies or something, and come up with some way of.
Well, I mean that's a whole there's a big field in simulations who are trying to figure that out.
Mm-hmm. That's why I asked the question.
And you basically need much better resolution. There are tons of people working on improved subgrid models because we really won't be able to afford the resolution that we need in the next decades, probably. I mean, there's no way I can answer that question, of course. But I'm working on it. maybe before I retire, I can answer.
You're young yet. You have time.
Yeah.
Room for growth. Goodbye.